All right, so in the previous video, we were looking at just sort of the basics of nuclear chemistry in terms of the different types of decay. So if we've got these unstable atoms, there's multiple ways that they can kind of break down into a more stable product. And then what we'll look at today is kind of the reason we see those different types of decay, so alpha versus beta versus electron capture, whatever it may be, with those different types of decay. And we'll also see that in some cases it's going to be kind of a chain reaction. So it's not just going to be a single decay, but there's going to be multiple steps until we ultimately go from whatever that radioactive atom is to a stable one. And what we're looking at here to start, just make sure I'm on the correct slide. Oops, yeah, okay. So looking at the graph here, this is just representing on the x-axis the number of protons, so the atomic number. So as we move right one, we're going from hydrogen to helium to lithium, beryllium, so on. And then we have it up to atomic number of 80, so we can see mercury, but we're missing the last little bit of the periodic table, those larger atoms. And then on the y-axis, we just have the number of neutrons. And we've got kind of two different pieces to this because we've got the red line just showing the 1-to-1 ratio. So for every proton, we would just have a single neutron there. And then we kind of have a slightly lighter sort of shaded area with a bunch of dots in it. What these dots are representing is the stable nuclei for all of these different elements. And then what we're going to refer to this sort of shaded piece as is just this belt of stability. So we're going to see that's going to be the location, the combination of, or the ratio of, I should say, neutrons to protons, where we're going to see the atoms themselves are going to be stable. And the reason we have this is because once we get to atoms bigger than hydrogen, now we're going to have multiple protons, so we're going to have multiple positive charges. So we're going to see those positive charges are going to repel. So just remember, like charges repel. We see the same thing with negative electrons when we're looking at the Vesper model. So when we're determining the actual geometry of those molecules, it's based on the electrons pushing those different atoms, pushing those bonds in certain positions to reduce that repulsion. And we have a similar phenomena with the nucleus, where we've got those positive protons and those like charges are going to repel. But to keep the nucleus from just sort of exploding, all of those protons just being shot out in different directions, we have the strong nuclear force, and that just helps keep the nucleus intact. And then with this, the neutrons themselves, that's why we have this graph here, are going to play a critical role in that. Because if you think about it, if we had just a whole bunch of positive charges there, there's going to be a lot of that repulsion. But now if we can kind of sort of intermingle the neutral neutrons, they kind of serve as a buffer, help reduce some of that repulsion. And we're going to see, based on the ratio of those protons to neutrons, or more accurately, neutron to proton, as it's shown here, is going to be a critical factor in terms of whether that atom is going to be stable or not. So the ratio of those two subatomic particles relative to one another is going to be what we're looking at with this belt of stability. And we can see with the earlier elements, so those smaller ones from about hydrogen up to calcium, so atomic number of 20, we can see for the most part, the stable atoms are going to be pretty close to that 1-to-1 ratio. So we're going to have a single neutron for every proton. And if we just think about oxygen, the most common isotope, oxygen-16, 8 protons, 8 neutrons. Same thing with nitrogen, nitrogen-14, 7 protons, 7 neutrons, carbon-12, 6 and 6. So with those smaller atoms, we see a 1-to-1 ratio between those subatomic particles in the nucleus. That's going to be the most stable ratio there. But then as we get to slightly larger atoms, and then even all the way continuing up to mercury, as we get more of those positive charges, now we're going to need more of the neutrons to stabilize that nucleus. We've got more of those positive pieces, so we need even more of the neutrons to kind of buffer those positive charges from one another. And that's why we see, as we get above calcium, as we get above 20, we start to see that ratio increase. So with this belt of stability, we no longer just see that straight line on the 1-to-1. We see it starts to curve up, and we get an increasing slope. And that's why if we just look at the examples here, zirconium, atomic number of 40, tin, atomic number of 50, and then mercury, atomic number of 80, we can see just as we increase the atomic number, as we increase the number of protons, in order for that atom to stay stable, we're going to need to increase the ratio of those neutrons as well. So early on, it's 1 to 1. With zirconium, we have a 1.25 to 1. So in this case, we've got 50 neutrons for 40 protons. So 1.25. Tin, we see it increase even further, 1.4 ratio, because now we've got 70 neutrons for every 50 protons. And then all the way up at mercury, we've got a ratio of 1.5 to 1, because now we've got 120 of those protons, or 120 of the neutrons, excuse me, versus 80 of the protons. So just as these atoms are getting larger, as we're getting more of those positive pieces, we need even extra of the neutrons in order to kind of keep that nucleus together. And as I mentioned, and as it says it on the graph right in the middle here, this is just referred to as the belt of stability. So that's where we're going to see those stable atoms that aren't going to undergo that radioactive decay. And then with this, if we think about the radioactive isotopes, the ones that are going to be either below or above this belt of stability, the position relative to that belt of stability is going to help us predict what type of decay it's going to undergo. So for a moment, just take a second to think about if it's above the belt of stability. In this case, what that represents is we've got too many neutrons now relative to the protons. So we want to think about what type of nuclear decay would kind of help alleviate that situation. And then a similar idea, think about if we're below this belt of stability, now we have too many protons or not enough neutrons. We can kind of think about it from either perspective there. Think about what type of decay we could kind of undergo to move that atom into this belt of stability. Because remember, with the radioactive decay, we're taking that unstable atom and having it break down into something that's going to be more stable. But again, with the top one here, if we're above this belt of stability, now we've either got too many neutrons, if you want to think about it that way, or not enough protons. So in that case, what we're going to see is the atoms above the belt of stability are going to undergo beta decay. And with the beta decay, remember, that's going to be essentially just ejecting an electron from that nucleus. So in the case of the beta decay, we're not changing the mass at all, but because we're getting rid of a negative charge, it's essentially converting a neutron into a proton. And if we had too many neutrons to begin with, changing one of those into a proton is going to get us back into, or get us at least closer to this belt of stability. So it's going to help us get a more stable atom in that sense. And then with the atoms that are below this belt of stability, we'll see the opposite. In this case, we've got too many protons. So with these ones, there's actually going to be two different forms of decay they can undergo, ultimately resulting in the same thing, ultimately kind of just converting one of those protons into a neutron. And then those changes are just going to be, hopefully you didn't hear that email noise because that just scared me. But the changes here we're going to see are going to be changing a proton into a neutron, because now we have too many of these protons. So we're going to see this can occur either through electron capture. So that's the radioactive decay where we've actually got the other piece as a reactant rather than a product, or positron emission. Both of those are going to result in the same thing. Both of them are going to result in essentially a proton getting converted into a neutron. And then if we have too many protons, that's going to help make that atom more stable. And then with this again, we just go back for a second. So in this case, we can see up to atomic number of 80. So we can see mercury. We could also have thallium. We could also have lead. And because those have 81 or 82 protons respectively, those could be stable nuclei. Of course, it's going to, again, depend on how many neutrons we have along with it. But if we have an atom that has 83 or more of these protons in its nucleus, that is always going to be a radioactive nucleus. So it's always going to be unstable. But with that, just note that the instability doesn't necessarily mean that it's going to break down right away. So with atomic number 83, that's going to be bismuth, Bi. So I'll do 83. and then 209. All right. So with bismuth, I think it's bismuth 209. I didn't write down the actual mass there. But there's going to be an isotope of bismuth, and then since it's got 83 protons, it's going to be unstable. It's going to undergo radioactive decay, and we'll see these larger atoms are typically going to undergo alpha emission, so they're going to release that helium nuclei. But with the bismuth 209, its half-life, and we'll talk about half-life more later in the quarter, it's essentially just a measure of how long does it take for 50% of this radioactive substance to decay into whatever that product's going to be. We'll see with the bismuth, or at least with one of the isotopes of bismuth, the half-life is going to be on the scale of 10 to the 19th years. So it's going to be a tremendous amount of time. So for all intents and purposes, it's a stable nuclei, just because we could still do whatever we want with it. It's not going to decay in a time frame that we're going to be able to notice, but it is still going to be radioactive. It is still going to undergo that decay. So we would still classify it as an unstable nuclei, even though it's going to be able to basically exist for an unfathomable amount of time. But once we get 83 or more protons, that nucleus, you can kind of just think about it as now we've got just too many of the positive charges no matter what. So that nucleus is just going to be unstable. It's just going to ultimately undergo that decay. And then with some of these, we'll talk about them later on, especially with the elements that are man-made. A lot of those are kind of just used to prove that we can make them. And we'll talk about the process in this chapter as well of how that occurs, how a man-made element is created. But a lot of those are kind of just made for the purpose of showing that we can do it. They don't really have any useful application. And in some of those cases, the atoms themselves only are stable enough to exist for like fractions of a second. But in the case of bismuth, we kind of see the opposite end, where it's going to be able to exist for an extremely long time. Eventually, though, it will undergo that radioactive decay. Whereas the stable nuclei of the smaller atoms can basically just kind of hang out for as long as they want, as long as we don't have some sort of chemical reaction take place to form into a compound, and in which case it's still going to be that same atom, or if we subject it to a nuclear reaction ourselves. And as I mentioned, a lot of these radioactive atoms are ultimately going to undergo decay in order to get a more stable nucleus, form a more stable atom. But with a lot of them, we'll see kind of similar to what we have on the graph here. It's going to be a chain reaction rather than just going from, in this case, uranium straight to lead. We're going to have a series of reactions. A radioactive series is what it's known as, where we transform, in this case, uranium into thorium, into protactinium, uranium again, into a different isotope of thorium, radium, radon, polonium, lead, bismuth, another isotope of polonium, another isotope of lead, another isotope of bismuth, another isotope of polonium, and then finally this stable version of lead. And with these types of series, a lot of the times we'll see that the final product, so that stable nucleus that we're going to produce in the end of the series, is often going to be lead. Not 100% of the time, but it is a fairly common sort of product of this type of series here. And then if we think back for a second to electron configuration, we had different configurations that were more stable. So of course, the noble gases, that fully occupied valence shell. But then also there was the completely unoccupied or the half-filled. Both of those were more stable than other configurations. We're going to see something similar here with the number of protons and neutrons. There's going to be certain numbers that are just going to offer increased stability relative to other examples. And with it, if we just think about that lead again, a lot of the heavier radioactive substances that undergo decay are going to result in a lead atom ultimately. So we're going to see nuclei that have 82 protons. which is just Pb for lead, is going to be one of those conditions. And then we've got a series of other ones, so 2, 8, 20, 28, 50, and 82 for the protons, or similar numbers plus 126 for the neutrons. These are just going to be, like I said, more stable. And because of that, we refer to these as magic numbers in chemistry, or physics even too. And then with it, you can kind of think of, again, with the electron configurations, we always had those electrons in pairs in an orbital. And then that fully occupied orbital was more stable. So what we actually have with the neutrons and the protons is something similar, where we actually kind of have a shell model where we'll have these substances paired together. And again, that's just going to offer increased stability. So with these magic numbers, if we have an atom that has 82 protons, likely to be more stable than if we had an atom with 81. And then again, above 82, so 83 or larger is just automatically basically going to be an unstable, a radioactive nucleus. And then with it, you can see here, all of these are even numbers. So when we look at the combination of protons versus neutrons, we can see most of the stable isotopes are going to have an even number of both of those. And then we can still have a decent number of isotopes that'll be stable if we have one of those being even. So if we had an even number of protons or an even number of neutrons, and then an odd number of the other, we still have a pretty good amount of those isotopes being stable. Because again, we're still kind of thinking about these subatomic particles as pairs, just like we did with the electrons. It's just in this case, we're looking at the nucleus. But when we've got both of these subatomic particles, the number of these subatomic particles being odd, we've got very, very few actually stable isotopes there. So with these ones, just remember the numbers we're representing here. I'm not going to, with the exception of 82, just for lead, I'm not really going to expect you to memorize these. I don't think having the specific magic numbers memorized is an extremely useful exercise. But we just want to, and the reason I'm picking 82 is because just that's going to be the threshold for once we get above it in terms of protons, it's unstable. But we just want to recognize the pattern here with even and even is going to give us the most stable, because we'll have these nucleons in pairs essentially. So just to wrap this video up, we'll look at a couple examples where we're trying to predict what type of decay these different substances are going to undergo. And with it, I put the belt of stability, that diagram, that graph on the right-hand side. So if you want to take a moment to look at these two examples, and then we'll have two more after this as well. But with these ones, if you want me to kind of demonstrate how we would approach these ones, you can practice with your own on the next ones, or you can pause it here and just practice with both sets of these types of questions. But with the examples we have here, we've got carbon-14, xenon-118, and we want to determine what type of decay. So we've got alpha, beta, gamma radiation, positron emission, electron capture. So we've got those different types of decay. And then with the belt of stability, we can use that to essentially kind of locate where this isotope would be relative to that belt of stability. And then if it's above it, it's likely to undergo beta decay. If it's below it, it's likely to go either electron capture or positron emission. Both will ultimately result in the same product, just through different paths, kind of. And then if it's to the right of this graph in terms of protons, with the exception of just 81 and 82 for thallium and lead, it would be likely to undergo alpha decay. So in this case, with carbon-14, we know the mass, 14, and then since it's carbon, if we have our periodic table, or if we just have it memorized, we know there's going to be 6 protons there. So we're going to have 8 neutrons to give us the mass of 14, along with those 6 protons. And then we could do the same thing with xenon, mass of 118, but since xenon is atomic number 54, that means we'll have 64 of the protons. So if we look at the ratio here, neutrons to protons, 8 to 6 for carbon. And remember, these smaller atoms typically want that 1-to-1 ratio. So in this case, we've got extra protons, or extra neutrons, excuse me. So we're going to undergo beta decay. In that case, our carbon, I should say, is going to undergo beta decay there. So it's going to emit that beta particle is going to emit that electron from the nucleus. Not going to change the mass at all. So we still have 14 and 14. But because we're losing that negative charge, it's essentially converting a neutron into a proton. So we see the atomic number increase. And we're going to see the product here is just going to be nitrogen. And then with the ratio here, 1-to-1, that's going to be a stable nucleus. So for this question, we were ultimately just looking for the type of decay, but we can also use that type of decay to then determine what that actual product is going to be. And remember, we just need to have the mass numbers balanced. So we've got 14 across the top on both sides, and then we need the atomic numbers balanced as well. So we've got 6 across the bottom here. And then with the second one, we've got a ratio of 64 to 54. So this is going to be 1.2 neutrons to every proton. So if we look at our graph, 54, we can see tin itself has a ratio of 1.4 to 1. We're even further to the right, so we should see that ratio increase slightly as we go from tin to mercury, so 1.4 to 1.5. So if we're at 54 now, we'd expect it to be a little bit above 1.4. But since it's at 1.2 to 1, that means we have too many protons. So we're basically going to convert a proton into a neutron, and then we can do that in 2 different ways. So the reaction on the left here, and you'll notice in both cases we wind up with iodine 118. But with the reaction on the left, this would be an example of positron emission. So we're ejecting that positive electron basically. So we've got a 1 here rather than a -1 like we had with the beta decay. Or we could have this nucleus essentially accept an electron and just convert that proton into a neutron and still wind up with 118. So when we're below the belt of stability, we'll have that atom either undergo electron capture or positron emission, whereas if we're above it, it's likely to undergo beta decay. And again, just think about where the location, what that means relative to the belt of stability. If we're above it, now we've got too many of these neutrons. So beta decay will allow us to convert one of these neutrons into a proton rather. Or if we're below it, we need the opposite to occur. And that's why we see the mass is still 118. But in this case, we have the atomic number decreased by 1, so 54 to 53. And then if you want to practice with these two, just pause the video again. But it's going to be kind of the same idea. And with the first one, plutonium-239, in this case, plutonium is going to have an atomic number of 94. So it's larger than lead, likely to undergo alpha decay. So we don't really need to look at the belt of stability in this case, just because we have a whole bunch of protons there. So anything above 83 or above is going to be unstable, likely to undergo alpha decay. That's what we'll see with plutonium-239. And then with the indium-120, we've got an atomic number of 49. So that means we're going to have 71 neutrons. And that's going to be a ratio of 1.45 to 1. And with this one, we're going to be just left of tin here. So we'd expect a ratio just about 1.4, maybe a little bit under. We're a little bit over though, so we'd actually be slightly above this belt of stability. So if this indium atom was to undergo a nuclear decay, it would likely to be beta decay. So our product in that case, since we're going to be converting a neutron into a proton, 49 to 50, because we're emitting that beta particle, we'll see that the product is likely to be tin. And then remember the magic numbers, 50 is going to be one of those. I forget what we had for the other ones here. Yeah. Okay. But with the next section, we'll start to look at how we can kind of, in a laboratory, sort of start to induce these types of reactions. So up to this point, we've been kind of looking at natural radioactive decay, so things that are just going to, on their own, essentially, break down according to these different processes. But what we'll start to look at next is how humans have kind of harnessed this ability in the laboratory setting to create these types of reactions.